Hi, I'm Flora Salim. I'm a professor at School of Computing Technologies at RMIT University and also a deputy director for the Center for Information Discovery and Data Analytics. And today I'll talk about how can we learn human behavior representation from sensor data that are generalizable as well as transferable. Now, why is this an important research or problem? Well, now there's so much wealth of sensor data around us that actually provide a lot of opportunities for us to derive insights about human behavior. And this sensor data can exist from the smart devices that we're all using these days. The wristwatch watches to smart speakers at home to Internet of Things around us in the city, in smart grids, and also in smart health and digital health monitoring. Now, what just giving you a brief examples of human activity recognition, which has been more than a 2 decades problem in the area of ubiquitous computing and pervasive computing, and typical hard problems include physical activity recognition. So from the sensor data that you see on the left is trying to actually understand whether someone is actually standing, walking, running, jumping, for example. So this is useful, for example, for step counting on your smartphone, or from census data, it can also try to recognize, for example, gestures that people are using in order to interact with certain devices. And typically in the area of ubiquitous computing, non-visual multimodal sensors are used as input. Obviously, vision sensors can be used. Cameras as input can be used for example, action recognition, which is an established problem as well in computer vision. But today, my focus is basically the use of non-visual multimodal sensors that I like to focus on. Now, behavior recognition is actually slightly more complex because this actually involve cases where you actually need a lot more sensor data to understand complex behavior such as emotions or the tasks that people are doing at the moment, or try to infer the information needs or the information intent of users. So just for terminology's sake, I'm just going to talk about human behavior recognition in general. So how we then recognize human behaviors with heterogeneous sensor data that are already deployed in the wild. So what I mean by in the wild is typically sensor data are captured by the one who actually deployed the sensors and collected them for a specific purpose. But let's say we manage to tap into sensor data that can be collected in the wild without even any supervision. How do we actually leverage them for all kind of purposes that even beyond the original purpose it was actually designed or collected for? Now, I already mentioned this, that understanding human behaviors is important to improve the efficiency, sustainability, and health and safety for a lot of operations in smart cities, smart buildings, and a lot of other industry verticals. So what is the typical pipeline for behavior recognition? Well, first, you actually have subjects that you like to monitor in a daily environment. So it could be human, it could also be animals, it could be also systems, so it could be also machines. So, but for argument's sake, let's talk about monitoring human activities, and we like to actually based on the tasks that we like to monitor. Say, for example, just want to monitor and ensure that this elderly is actively moving and trying to detect fall, for example. So you may deploy certain types of sensors suitable for that problem. And once you deploy that sensors, either getting the users to wear the sensors or installing them in their home, you start collecting the data, and it's very important to perform annotation or label the sensor data once it's collected, because you need to then use the data to train a model or to validate your model. And this is a typical machine learning pipeline. Here you have a pre-processing step, And noise removal and filtering here is often very critical, especially for sensor data, because sensor data is very noisy, and I'll get into that later. And you have the typical feature extraction and selection step as well, before we get into the fun part, which is deploying machine learning techniques or the deep learning techniques to infer activities or behaviors. And once you actually have got a couple of models, you learn and train, you evaluate them, you choose the best ones, you then actually extract insights from the models, and then you then decide to deploy the model that will be best to suit a certain task. Now, obviously, this is a really long pipeline, and we can see there's a lot of bottlenecks in right up front. For example, the bottlenecks of actually deploying sensors, because this actually takes time to deploy sensors. It takes resource, time, cost, and also the first sensors may not be correct for the purpose of the task. And there's another major bottleneck, which is the data collection or annotation labeling of the collected data. And the reason why is because the labeling sensor data is very, very difficult. And that's why often in this case, even when you deploy sensor data in the wild, you actually still need cameras to capture video feed of the users in order to be able to correctly label activities and behaviors. And often things even are not observable by videos, for example, emotion, right, or sleep stages and things like that. And so this is actually still a very difficult problem, and it's a bottleneck for a lot of activity and behavior recognition tasks. And preprocessing is also very difficult because of the noise, and I'll get back into that noise issue. And let's say if you actually manage to deal with the bottlenecks at the early stages of the pipeline, we come into the aspect of the machine learning model. They are typically fully supervised, which means it really needs lots of labeled data in order to come up with models that are reliable and also effective. And this actually then leads to the problem that is not only expensive, and also because it's normally require domain expertise, because, for example, trying to label sleep activities or trying to understand somebody's physiological signals, it requires people from that domain to help the annotator to actually annotate the data properly. And also often it's the labels are narrow or designed only for that specific task that is trying to be modeled, and therefore a lot of machine learning models in this area are actually aimed at single task problem. So not only due to the limitation of labeled data, but also it's basically designed without being able to be generalized. Now, let's consider that the sensor selection problem is solved because, well, if we can tap into a lot of different sensors in the wild, we'll talk about privacy issues later on, but let's say we can handle this. We can actually, let's say, tap into the sensors on somebody's smart devices. Let's say this person here trying to understand trying how to get from here to there, from A to B, or trying to actually find information about their next meeting. And how does a smartphone actually can provide information that can help her in her current information need? So can that be inferred from existing sensors? Can it be can there be a model that actually learn their past behavior in order to predict the future behavior of this user, for example? Now, so let's say this is done, but still the other bottleneck still there. So because if the data is collected in the wild daily, regularly, there are lots of data and they're not labeled. Nobody will actually be monitoring this person to actually know what's going on. And to add further complexity is And also there's opportunity, not just the challenges, but also the opportunity that there are a lot of sensors in multiple domains, from manufacturing to transport, for example. So for example, trying to understand the behaviors of machines, trying to actually recognize, for example, public transport modes and also where it stops, or if there's any anomalous behaviors in systems, in agriculture or in energy and grid system, for example, or trying to understand retail behavior. There's a lot of different opportunities that can, that can leverage the proliferation of these sensor data. But obviously, there's also a lot of different activities and behaviors that are possible that can be learned from these different sensor data. Now, because of the wide variety of inference tasks, I'm just giving you a couple of examples here. These are some examples of inference tasks you can see on the list that we have actually done in our lab. So physical active recognition, step counting, for example. So those are to do with physical movement, including, let's say, transport usage, mode prediction, and do things to do with psychometrics, say, personality prediction, to emotion and stress recognition, and productivity, whether someone is productive at work, and trying to actually also predict things like cyber or online behavior, like app usage or health condition. So there's a lot of different activities that could be inferred from sensor data, a lot of behavior that can be inferred. But not only the variety of labels are making it more complex, but also the data itself is very challenging to deal with. If you think about sensor data collected in the wild, they're typically heterogeneous, which means even this, these sensor data, they can have different sampling range unit, and the frequency of data that are collected are really vary. Because people deploy it for their reason, and when we use it, it may not be available all the time. So there's a lot of missing data potentially, and data is as well can be really noisy, which means in two aspects. The data is noisy because the same sensor, let's say accelerometer or temperature sensor, even from different manufacturers, the quality can vary, and the label can be noisy. So if, let's say, you have an annotator that actually label what's going on, these labels can come from different annotators, and when they look at the data, they could actually annotate it differently. It's not like when you're annotating an image, it's an image of the dog. Everyone will know it's an image of the dog. But when you're actually annotating an activity, people can have different view. So the ground truth itself is questionable sometimes. It could be biased. And also the sensor data itself, because of the multiple channels, the high dimensional sensor data, they may have certain correlation, positive and negative correlation to each other, and they may the different sensors could be more useful for predicting certain tasks or certain contexts, but not for other tasks. So if you can see here on the right, there could be different label sets that actually belong to different activities or tasks to be inferred. Now, so why don't we just use deep learning, right? Representation learning on all these sensor data and let it actually just learn, and we don't have to do the dirty work. Well, the thing is, representation learning requires lots of label data. So representation learning comes from computer vision, obviously, which has taken a lot of advantages of the ImageNet, and people have been thinking about, what about ImageNet for sensor data? Well, the thing is, this is invisible because I already mentioned before, it's challenging to annotate sensor data, and it's time consuming, and in many cases, it's not accurate, completely accurate. So therefore, if we need to perform representation learning from sensor data, there are several criteria that we have to consider. The representations that are generated, they need to be compact, simply because if they need to be deployed, they will be deployed again back on these little devices. Often they don't have to be placed on a central server. They need to be representative, which means these sensor data need to be able to represent a lot of different activities for downstream tasks, so a wide range of downstream tasks. They need to be robust to noise, to change the dynamics and the sensor data, and they need to be reusable. So, which means if there is a model that has already trained, ideally it should be able to be transferred for other tasks. So that's why, because of these needs, there is a need for generalizable representation learning technique with unsupervised or data efficient learning techniques. And although there's already a lot of work in other domains such as computer vision or language models, there are not many available in our area in uses of time series and machine learning with time series for behavioral representation. So going beyond typical behavior recognition pipeline, we have to consider different techniques, and it all depends on how much available, how much annotations available in the data set and whether they are reliable. And think about how many examples are available for you to perform your training, and whether the techniques you have are need to be explainable or not. Some of our key strategies that we have performed in our lab and we have come up with includes time series segmentation, self-supervised learning, and basically the use of context information, so context-aware modeling, especially for transfer learning. Now, let's start with time series segmentation. So Espresso is a method that we propose that leverage entropy and shape-aware changes for processing heterogeneous sensor data. Now, when you consider segmentation, you need to the first thing to consider is we need to come up with homogeneous segments across multivariate time series. So these homogeneous segments across multivariate time series will signify behavior that have changed, so an activity that have changed. So what you can see potentially is somebody doing a certain activity A and then changing to activity B. So the change point is signifying a boundary of class that's transitioning from class A to B, or potentially it could be an anomaly as well. Now, this is quite an important, segmentation is quite an important task because it's useful for preprocessing. It's also useful for further tasks, for further downstream tasks. So now, a lot of temporal segmentation techniques, they focus on one aspect of changes, either changes on shapes or changes in the statistics, or they also can only work for certain types of changes, either they're repetitive or non-repetitive, or whether they're actually gradual changes or sudden changes. There's no single method that can handle all of kind of changes. And so we actually then come up with Espresso that combines two of the state-of-the-art methods that actually focus on the shape-based changes, which is floss, based on matrix profile, and also statistical changes, which is IGTS, which was our prior art prior to Espresso. And we actually combine the statistics and shape-based changes to come up with boundary segments, and then we compute it with this entropy rule. Now, these are the range of data sets that we have evaluated our method with. So, for example, we have performed segmentations on data sets for hand gesture recognition, physical activity recognition, data sets, multimodal sensing data sets for detecting stress, amusement state, for example, using ECG, EMG, EEG, and respiration state, and also emotion recognition data set. Now, as you can see in this slide, that Espresso as a hybrid method, a method that actually merged both statistical and shape-based approaches, outperform all the state-of-the-art, all the previous state-of-the-art baseline methods in almost all cases. There are some exceptions, and you can see that in some cases, GTS, which was our own method as well, works better, but this is actually quite rare, which is a data set that has sudden changes. RFID is a data set that with sudden changes and repetitive patterns. In most cases, you have data sets that are that have continuous changes or non-continuous changes. As you can see here, that espresso in red performed really well across all dataset categories. Now, in real-world case studies, we also found that espresso is also explainable because it can actually detect changes in work routine during weekdays and weekends, and also detect changes in emotions. So, and therefore we can also plot it across time. So we can then find out, for example, how much time is needed to capture changes in someone's emotion using a combination of wearable sensors such as ECG, EMG, and all that. Now, this is the link to the code. Now, there are a lot of different applications of serial segmentation. They include, for example, mobility pattern mining. So, for example, with the data on your smartphone, we have access to, for example, GPS connectivity to cell tower, Bluetooth contact traces around us, sensor data, including the IMU, the magnetometer, the barometric pressure, the temperature sensor, and all that. And with that, we can actually perform segmentation at multiple granularity, multiple resolution. So, say, for example, on a high level, you want to predict first changes within someone's daily pattern, what time they actually shift from home to university and university restaurant, for example. But in the fine resolution, you may want to know, for example, when they move, what sort of activity they're doing. And for example, when they're in the university, which access point, Wi-Fi access point they're connected to, and can we actually predict where they will go next or what they will do next? So if you combine, for example, the temporal segmentation approaches that we have, and with some kind of similarity search and ranking, you then can actually then search for the most similar activities or trajectories in the past, and you can then stitch them together in order to predict the trajectories, the location and time they will go next in the future, as well as activities, trajectories of activities in the future. So this is the continuous trajectory problem that can be solved using segmentation combined with similarity search. And this is actually applicable for both geographical and labeled trajectories. Now, basically, segmentation can also be used for pre-processing techniques. So in here, for example, we have a really big data set that we collected in high school. It's actually consisting 5 months of indoor and outdoor weather station sensor and building sensors, windows and aircon sensors, and also 4 weeks of cross-sectional study with the teachers and students wearing the wearables. Now, let's see the purpose of this study, but I'll play this video.
Imagine when you are giving a math class to students. Do you want to know? Do they pay attention in your class? Do they pretend to listen but actually not? Do they enjoy your class? Do they feel discouraged during the group discussions? Are they actively thinking what they are learning in class? Student engagement refers to the degree of attention, interest, curiosity, and involvement in the learning environment. Based on previous studies, as many as 40 to 60% of high school students are disengaged, which may lead to the disaffection, low academic performance, and high dropout rates. In the United States alone, over 1.2 million students drop out of high school every year. That is to say, 7,000 students a day and 1 student every 26 seconds. Student engagement has 3 dimensions: emotional, behavior, and cognitive. In our research, we collect data from daily survey, indoor weather station, and wearables using multiple sensors in a private high school. We use sensor data as input, then apply preprocessing techniques to build machine learning model to predict the multi-dimensional engagement for students. Our research provides opportunities for the future design of feedback systems in the classrooms and have potential to benefit both teachers and students.
So as you can see, it's a really big collection of really high-dimensional multivariate sensor data from many classrooms and also many participants. Now, the usage of segmentation here is really critical because of no video use at all. So there was no label at all in the sensor data. So we actually need to use a segmentation to actually, let's say, for example, segment the class. So we know there's a session of a class, for example, and we need to know, for example, activities that happen across the students or within each of the participant and across the participant in a class, for example. And the usage of segmentation is really critical in this step and data processing step. For details of the paper, please read the paper again. So now I'd like to talk about representation learning of time series without using labels. And so to continue our work on time series change point detection, we also have employed contrastive predictive coding, which is a self-supervised learning technique. So many anomaly detection and also activity and behavior recognition tasks, as I mentioned before, are fully supervised learning normally. Typically, they are approaches to supervised learning approaches. But can we actually detect the changes in these activities and can we actually detect anomaly in self-supervised learning manner? And therefore, we're actually learning from the instances itself as an example. And we basically perform augmentation on of the time series instance, and we perform negative mining on this approach, and then we combine it with basically reconstruction loss that is suitable for a time series problem, because a lot of reconstruction loss actually only fits for vision-based learning. Now, and also another gap is a lot of approaches are not quite general for all kind of time series. So our contribution is a way to embed this representation, time series representation, and we come up with predictive coding approaches that can work for time series change point and anomaly detection, and also contrastive learning. So the goal is then we extract representative feature factors from these semantic segments that enable change point detection. So this is actually the architecture. I won't go into detail. Please take a look at the W paper from this year. And as you can see here, TSCP2 actually outperform all the baseline approaches, including the deep learning approach, KLCPD, that was it was actually claimed as a self-supervised, but actually required label data in training. That was from NeurIPS 2020. And we performed evaluation on Yahoo benchmark dataset for anomaly detection and also human activity recognition dataset. Another work that we did where we actually leverage self-supervised learning technique is this paper that's actually going to be presented in KDD, also in this conference, where we actually explore self-supervised and representation ensembles. They actually train with unlabeled sound signals collected with smartphones. So there's already a lot of apps since the early pandemic in 2020, apps they are deployed to collect the sounds of COVID. But of course, then you need well annotated cough labels, whether this is COVID or not COVID. But can we actually then use any of these unlabeled sound data to just pre-train a model in contrastive learning manner? So in here, we didn't use any labeled data. And in the downstream phase, then we actually use the label data to perform the cough classification. And for the detail, please again take a look at the paper on the contrastive pre-training stage and also the downstream classification phase. So we then retrained this on a large-scale IIS Coursewire data set, and we tested this on COVID sound data set collected by Cambridge. And also one more work that I like to highlight is the usage of self-supervised learning, because it can come up with compact representation without any labels. This can actually be used to train local models on the edge, which then comes back to my comment earlier that you can then make this privacy preserving, because you can just, the data do not have to leave the device. The data can be trained on the edge as local models. And then we can have the central aggregation server that actually, where it actually pulls and compute the shared average of the weights of the model computed on the edge, and use it to improve the central model for end tasks. So this is actually the first self-supervised learning that are actually done on the edge and also federated and published in Internet of Things Journal last year. Now, finally, the last technique I like to mention is the need to use of contextual information if you want to perform transfer learning, especially if there's not much data available in the target domain. So context is important because context can actually give us semantic information that reflects the decision-making process, or it could actually reflect different behavior of users or even systems. Now, if you don't have label, one information where you can get the meaning of activity or behavior is from the context. We could look at the distribution of the data, distribution of this context. Say, for example, activity. Look at the normal distribution, or look at the, for example, if you want to look at the social context, look at the multinomial distribution across the subjects you like to observe. And in here, this is what we did in this paper, where we performed a few short transfer learning for parking availability prediction. So here's an example, right? So we have data from Melbourne CBD. We have more than 5 years of parking data. And there are tons of papers on predicting parking availability using lots of data from Melbourne CBD. But we have this large-scale government-funded project for smart parking in Mornington Peninsula Shire, including Rye Township. And as you can see here, if you're not familiar with Melbourne, it's a tourist town, it's a small town. And when we managed to get the sensor deployed in February, in March, we had COVID hit, and then we had the lockdown and all that. So we only had literally a few days of data that are actually quite reliable, because after that, the behavior kept changing. So, for example, in this paper that we had published earlier, we believe the context information is so important to predict parking behavior, such as temporal context of weekdays morning or weekend afternoon, and also location, the context of location based on the POI information. And therefore, if let's say we want to perform a parking availability prediction that will be reliable and robust for Rye Township without much data, is there a way where we can actually not just use the physical parking sensor data, but let's also use implicit sensing technique, which is using auxiliary data such as weather data, POI data, demographic data, and try to see if any of those behaviors that are they are learned from Melbourne CBD can be transferred to Rye Township with few-shot adversarial domain adaptation. That's actually the idea. So here's some insights, some of the characteristics of the data set. So we have almost 36 million records from Melbourne CBD, but for Rye, it's less than 180,000 records and actually less number of these devices. And there's a lot of different kind of contextual information that we can actually collect it from the two cities. We then come up with this architecture, which is adapted ADDA, facial discriminative domain adaptation for this problem, where we perform pre-training on the source data with the historical data. And in the adversarial adaptation stage, we actually did not use the historical data. So we only use only a few days of historical data in the target. I'll just show you the result. So in here, just have a look. If you're interested, you can have a look more at the paper. But if you use full parking data without domain adaptation, and then when you compare it with using domain adaptation with only 6 days of parking data, it actually can perform quite well. It's only a small drop in error. So we learned that adversarial learning is really good at learning shared feature spaces, especially if we can tell the discriminator to learn from the contextual information. Now, in conclusion, we can overcome these major bottlenecks when we come up with techniques that do not rely on label data, especially using unsupervised learning or self-supervised learning, or if there are only very few data in the target domain, can we actually learn? Can we actually pre-train the model from using other data sets that have been collected before? So there's still a gap in our existing findings and techniques that we come up with. For example, still something to do with multitask learning. So how do we actually perform a generalizable model that can be used for different tasks? This is an ongoing work. And also, what about the use of multimodal, multi-source sensor data? So not just sensors, but when you start embedding languages, or when you start embedding multimedia data, this is also an ongoing work in our lab. And how do we learn novel behaviors on individuals, on groups, on populations in different manners, either few shot, zero shot, on continuous learning? Why? Because there's a lot of new behaviors emerging due to COVID-19 and all the different restrictions. So behaviors do change. So how do we actually learn these novel behaviors? So that's it for me. And I really want to thank all the great work by my students and my postdocs. And I also like to thank my collaborators on my projects, and also the funders of our projects. Thank you.
Thank you. Thank you, Flora, for sharing with us all the interesting insight about going from the low level, all sorts of insensitive data, to the high level human behavior modeling. I have a few questions for you. First of all, when we are talking about this sensitive data, oftentimes we are given the data first, then we're trying to do machine learning algorithms and understand this behavior. Do you have any thing to say about how are we going to decide where to actually deploy these sensors in the first place, or any of the findings that will guide us to maybe have a better way to actually collect the data in the first place?
Thank you for the question. I think it really depends on the problem, whether you want to actually monitor an area or region, or you want to monitor individuals. Do you want me to talk in general, or specific aspects?
Oh, let's say, for example, if we are modeling human behavior, right? Let's say collecting behavior sensor data. So you might have some devices collecting different, behavior data. But for example, where to put these sensors, and maybe where could be the best place to put the sensor, things like that. Yeah.
Thank you. So I guess the first thing to do, the first thing to understand is basically whenever you trying to design an ideal or optimal sensor deployment, we need to first understand that the first deployment strategy never is the optimal one. So we need to first always get a good sense of what the data looks like for different individuals and also different areas. So for example, if you want to monitor, air quality or CO2 in the room, for example, right? Or in hospital setting or in aged care setting, even if you place it near the window or near the door or near the HVAC outlet, they all are different. It will give you a very different reading. You might think your sensor's buggy or it's noisy. Well, it could be also very to do with the way you place a sensor. So yes, understanding that is important. And also, if it depends on basically wearable sensors, if it's a wearable sensors, a sensor worn on the wrist, and sensors actually you rely on just mobile sensors that could be placed in someone's pocket or someone's table different days of the it's all going to give you a different quality of data and readings, and therefore it is important. That's why, as I mentioned in my talk, modeling the context around the activities and the target task you want to model is very important. So, and that contexts are very rich. Spatial, temporal, activity context, and environmental context, they're all very different, and then they can have a very different influence to the sensor data.
Thanks. The other question is, because we're talking about human behavior, and many of the human behavior is in the context of social interactions. So do you have anything to say about how to leverage some social interactions, people's network, group behavior can contribute to the understanding?
Thank you for that question. Actually, because of the talk period is so short, we didn't have a lot of chance to talk about this work. There's actually, because of the use of mobile phone sensing, for example, you can tap into a lot of ways in modeling group behavior and social network through physical encounters or physical collocation. You can use it. You can use Bluetooth, that has now widely been used for Bluetooth contact tracing. So we have papers on that, for example. You can also look at regularity of behaviors of how people actually meet, that kind of social behaviors, and come up with a semantic constructs of what the different groups actually mean based on encounters, for example, in Wi-Fi networks or maybe cell tower networks, which you can actually capture also from logging this data on a mobile device.
I see. Great, thanks. So maybe the last question is, we have many of your work is working on trying to do prediction, and then I understand a lot of prediction is used to maybe raise some early warnings to something, to a quick response to some situation. So do you have any thing to say on how these early detections, what will be important in deploy this early detection rather than those retrospect, behavior? Yeah, I understand. Yeah.
Very good. So I think with regards to early detection, it is important to know how far or how early is your prediction horizon. So and it's also that actually requires a good way of actually modeling your representation. How long and how short is your representation in the model, right? So you may need to somehow, for example, if you want to have an early detection for earlier horizon, and things have changed really rapidly, you need to actually store that in your memory somehow, like your memory bank for your representation.
I see.
Just in case, there are unknown cases and unknown cases.
Yeah, I hope we have more time for you to share more work of the group. Thank you for giving us this nice talk, and thank you for attending KDD. I hope you enjoy the rest of the days here. Okay, thank you.
Thank you.
Thanks. Okay.